So lateral plate mesoderm. Some of this we're going to cover now. Others we're going to cover later when we get into the heart. Right now we're going to look primarily at how the limb bones form, and then we'll talk later on about heart and the blood vessels and the blood and the body cavity linings that come about from this. You can see that there's a lot of derivatives from the lateral plate mesoderm. So right now I want to talk primarily about the limb bones. So the muscle of your limbs comes from the paraxial mesoderm. The bones of your limb come from the lateral plate mesoderm. So this is why, when we talked about limb last week, you saw that both the paraxial and the limb, or the lateral plate mesoderm, these cells migrated into the developing limb, and that's really where they had their overall contribution, is the lateral plate mesoderm creates the limb bones, and the paraxial mesoderm creates the musculature of the limbs. And then the bone, the vertebral column, comes from the paraxial mesoderm as well. So there's two types of ways in which bone typically forms. You have what are called intramembranous ossification and endochondral ossification. Intramembranous ossification typically occurs in the head, where you do not develop an initial cartilage model. So one of the biggest differences between limb bone formation as well as rib cage is you'll form a cartilage model first, and then the cartilage will be displaced by the developing osteocytes, which are the mature bone cells, that will then calcify it and ultimately form the strong limb bones that you find in your forelimbs and the hind limbs. The intramembranous ossification, the cells migrate into their particular region, and they'll calcify and start forming the membrane to form the flat bones, say, of the head right away. And so you don't form this cartilage model, and then the model becomes displaced and forms a bone structure. It just goes straight to bone in that regard. One of the important reasons for this cartilage model developing first is because as the cartilage starts being displaced, eventually you're just going to end up with cartilage on the very ends of your bones. And that cartilage is necessary, especially when you're having bone-to-bone contact and a lot of the pressure when you get fluid in your synovial joints, to make it so that there's not any, rubbing. And that's where arthritis comes into play, is when you don't have that synovial fluid and you get the rubbing between the joints, and that causes a massive amount of pain. You don't have a huge amount of blood flow in between these joints as well, between the bones, which is why it's very difficult to have any type of repair and things of that sort when you get damage to that. So let's look at intramembranous ossification. When cells migrate into their particular region that are going to become bone, this process, the cells start building up a calcium matrix around them, and the cells will then mature, and we call those osteocytes. So the osteocytes are the ones that are the mature bone cells. Most of your bone, obviously, is calcium, but you do have cells that are maintaining that calcium matrix within your bone. Now, as far as intramembranous ossification works, the precursors to osteocytes are called osteoblasts. So in your bone, you have these osteoblasts that are building the calcium matrix. When the osteoblasts get surrounded by that calcium matrix, they will become part of the bone, and they will then maintain the overall bone density. They typically have these projections that come through the matrix of that to be able to get nutrients for the cells and to play their role in maintaining overall bone density. Here's endochondral ossification, where you form a cartilage model, and that's how we initially form. When our limbs form, when our limb bones form, they're just cartilage. They're pure cartilage. The lateral plate mesoderm, the cells that it contributes to the limbs, these are, as you get the stylopod, the zeugopod, and the autopod forming, these are going to coalesce and compact and start forming the humerus and the radius and the ulna and the metacarpals and the metatarsals and the digits and so on and so forth, and the femur and all those various bones. So we call them chondrocytes. These are the precursors that will form the overall cartilage model. They'll start proliferating and increasing in the overall size once they form this small model. Ultimately, this early cartilage model allows for the blood vessels and other tissues to ultimately associate with this cartilage model, especially when you're trying to get cardiovascular tissue to form the bone marrow that will start forming in the middle, where you're going to have these stem cells that are part of your cardiovascular system. So it needs to be a cartilage model initially, otherwise it would be almost impossible for the vasculature to be very, very tightly associated with your overall limb bones. The endochondral bones are primarily where you have your bone marrow, where you keep your hematopoietic stem cells, which regenerate all of your formed elements of your blood. So what happens is, here in the middle of the cartilage model, the cells will start creating a calcium matrix. This is during development. They'll start creating a calcium matrix, and they'll become osteoblasts. Okay, so they'll go from chondrocytes, which are the cartilage cells, and they'll start differentiating, and they'll become osteoblasts, which are the bone cells. So that's the big difference between cartilage and bone. Is cartilage we call chondrocytes, bone we call osteoblasts. These osteoblasts are going to build up the calcium that are necessary for the rigid bone structure. Eventually, the middle of it will start being hollowed out to make room for the blood vessels, for the hematopoietic stem cells, and this is really where you have your bone marrow. In fact, I've taken mice and done bone marrow transplants, and all we do is we strip them down, their flesh and their muscle, and we take their bones out, and we cut off the ends, and we actually just take a needle and we flush. That's how hollow it is. We flush all the bone marrow out to get their hematopoietic stem cells, and then we inject them into new mice to do the bone marrow transplant. So kind of fun. Anyway, so you can see how these plates actually will start progressing outwards. These plates play a key role, especially in adolescence, because these are the growth plates that when you have that growth spurt, you still have some cartilage in these regions, and what will eventually happen is the growth plates, which are the osteoblasts, will eventually overcome all of the chondrocytes, eventually overcome all of the cartilage, and then you stop growth. So it's a key point in development when you reach that growth spurt, because if you do not grow, which some people don't, they don't have the necessary hormones to cause their limbs to grow sufficiently, then you'll have stunted growth. And that's where human growth hormone comes into play, where some people may have some genetic abnormalities that prevent these growth plates from growing fast or from overcoming the cartilage model too fast, and then they're done. They can't grow out any further. That's really where we get into bone regeneration as well, is when you break your bone, there are osteoblasts that will recreate a cartilage model around where the break's at, and then then it'll reform that and recalcify it to repair the break and make it much stronger, because that's typically a weak point or a stress point in your overall bone. So the same process of endochondral ossification, of formation of the new bone, is actually the same process of bone repair that you find throughout your life. As you get older, the cells that are regenerating the osteoblasts get less and less efficient until, if you're old enough, a fall and breaking a bone can actually be very life-threatening, where your body will never repair itself. You get old enough and those cells won't regenerate anymore. A child can regenerate the bone to the point where you won't even be able to tell that they had a break. But as you start getting into adulthood, it gets less and less able to remodel the bone in the same fashion because of the degeneration of the overall stem cells. So that's ultimately how your long bones form, is they form this cartilage model. The chondrocytes will start proliferating, and they'll differentiate into osteoblasts. The osteoblasts are what cause the calcification. Some of the osteoblasts get caught up in the calcification of the bone, and they become osteocytes, which are going to be the mature bone cells that maintain the overall density of your bone. This is where stresses come into play as well. This is where environment plays a key role, is if because we're on Earth and because of the constant stress on our bone, that maintains bone density. But astronauts, when they go up into space, have to maintain a rigorous exercise schedule, because if they don't, their calcium matrix starts atrophying because of the lack of compression on their bones. And so they have to go through a really rigorous exercise schedule to maintain overall bone density. Hormones play a key role, especially when women reach menopause. They stop producing various hormones that are necessary for maintaining a bone density, and you start developing osteoporosis, where the bone density starts being lost at about 8% every 10 years for women and 3% every 10 years for men, primarily because we don't stop producing certain hormones. We just produce certain hormones throughout our whole life. And so that's why osteoporosis is more prominent in women than it is in men, because of some of the loss of hormones during menopause. So this just kind of goes through the progression of endochondral ossification. You have these chondrocytes, they proliferate, they form this model. Eventually they will differentiate into osteoblasts. Osteoblasts then get surrounded by the calcium matrix, and they become osteocytes. And that's really the progression of how cells start off as these lateral plate mesoderm cells and ultimately go through the process of becoming mature bone cells. So this is just this shows some of the genes that are involved in this process. And here's a showing of how your endochondrial bones actually form. The perimeter of your bones isn't just one large chunk of calcified matrix. It's actually cylindrical. You have cylinders upon cylinders in that. If you take a piece of paper, I always do this exercise with some of my kids where I give them a piece of paper, something like this, and I say, well, take this piece of paper and make it so that this is suspended, a couple inches off the ground, and they're doing this, and they're not figuring out that all you have to do is roll this up. So that's how your bone essentially is it forms these cylindrical layers of calcified matrix, and within each one of those layers, between each one of those layers, are the osteocytes. Now, they project parts of their cytoplasm out through this matrix, and that's where they get their nutrients. So you can see here we have the veins and the arteries that are kind of coming up right through the middle of these cylinders of bone. That's why your endochondrial bones need to start out as a cartilage model in order for the cardiovascular system to project the veins and the arteries into this structure. So your bone, most people think of a bone not as an organ, and it is. It's a living organ like any other organ in your body, where it has cells within each of these layers that are maintaining this calcium matrix. Without these cells, if these cells die, your bone degenerates and you're screwed. So within the middle of the bone, where you're, where you have your hematopoietic stem cells, it's a little different. You actually get more of this spongy bone forming, this irregular shape of these calcified processes, where it forms it looks kind of like a sponge. So it doesn't have the same cylindrical shape as on the perimeter of your bone has. In the middle, it just has this spongy looking, it's not spongy, but spongy looking bone, where you're housing your stem cells that will generate all of the formed elements of your blood. And that's what we're going to cover later on when we start talking about the heart and the cardiovascular system, is these hematopoietic stem cells that form from the lateral plate mesoderm that are in mainly your long bones, where you have your bone marrow. Here, on the peripheral of your bones, you have the periosteum, and this is where the tendons are going to attach to the bone, that then attach to the muscle that developed from the myotome, and that's what's going to give your body the ability to essentially move the limbs around, is that connection. If you didn't have the muscle, tendon, bone connection, you wouldn't have any leverage to move your body around the way that it does. Okay? So when the bone grows, it not only grows lengthwise, but it also grows outward. Now, there's another set of cells that develop called osteoclasts. The osteoblasts are the ones that create bone deposits. The osteoclasts are the ones that break it down. So one of the things about your bones is 99.8% or so of the calcium stored in your body is in your bone. And calcium plays a key role in muscle contraction and your nervous system. And in order for your body to maintain homeostasis, it needs to make sure that it has proper calcium levels going through the cardiovascular system. Well, one of the ways in which it does that is if you have not as much calcium as you need, the osteoclasts will break down some of the calcium matrix in your bone and release calcium into your body. If you have more calcium than you need, the osteoblasts will deposit that into your bone. So that's why you need to maintain regular amounts of calcium coming into your body, especially during growth periods, because that's where you're ultimately depositing a lot of this storage that you have in your bones, especially women when they're in their early 20s is where they have the maximum amount of deposits of calcium in their bone, which is why they encourage them to get as much as they can, because that delays the onset of osteoporosis due to hormonal imbalance later on. So what happens is it actually grows inward to out, where the inside gets broken down and the outside gets deposited, and that's how your bones essentially increase in their overall diameter. As far as the length goes, that's where the growth plate comes into play. Early on in development, you've got cartilage here, but later on when the bones is fully formed, the only cartilage you're going to have left is just right here at the junction between the two endochondrial bones. Here's showing kind of what happens during a bone breakage. So in parts of your bone where you don't have, maybe it's a little weaker, which is where the, a stress fracture or something else may come into play, you have osteoblasts that are going to rebuild around the fracture a new calcium or a new cartilage matrix. So this is where these cells will actually form a cartilage kind of model around the bone, very similar to how the cartilage model forms when you start forming your long bones. Eventually, this becomes calcified and will become bone again and surrounded by or engulfed by the osteocytes. So initially, when you reform or repair your bone, you'll actually see this little bump. If you were to look under a X-ray, you would see a protrusion or a bump. Over time, if you're younger, this will become smoothed out till it's just large and continuous, and you won't even be able to tell that that's there. But if you get a break when you're much older, this doesn't remodel itself as easily because of the cell's degeneration over time, and you'll have that for the rest of your life. It's just a tiny little protrusion or bump where that is. Ultimately, this is to reinforce the area where the break occurs, because that's where it's not as calcified or you got some weakness in that particular area. It's your body's way of responding to increasing the strength of that area so it doesn't break there again.